Okay, so since most students aren't here today, I'll have to start recording from the very beginning. Yes, for some reason it's still loading. One second. Is it not connected to the internet? Or looks like it is. Yeah, for some reason the EduRoam Wi-Fi is acting weird. Give me 1 second. Looks like it's still loading, as you see. But this is okay. It's doing all right. All right, I'll let it do its thing, but meanwhile, we'll get started and finish up the other discussion while this guy loads properly. Okay, so to begin with, I posted a pre-recorded lecture today deliberately. First of all, what if we don't get to finish it in time? Like a couple of slides, still remains. Then we'll have to come back all the way after the Thanksgiving on December 3rd to just finish up 2 slides. It doesn't make sense to make you go through that pain. So I decided to just pre-record anyways. And also to clarify, this lecture is not part of the final syllabus, okay? I'm only adding this to help you transition nicely and smoothly to 336, which is hopefully easier this year because we covered the labs. Most of this discussion about amplifier design and stuff are also covered in the lab. So if you have done the lab properly, hopefully you will be in good shape to move over to 336, okay? So, but I highly recommend, please listen to the recording. Don't just ignore it. Well, okay, it's not part of the final exam syllabus. It's probably going to take an hour and you could fast forward it. It's okay. Just make sure you go through it. I hope it will help. Second point is I will post a separate announcement with a special homework. And I also mentioned that in the previous announcement. And I know that you have enough on your plate. So this is going to be an optional homework, meaning you don't have to submit it if you don't want to. But if you go through it, this is probably going to give you a really nice overview of how to make an actual MOSFET from scratch in the most advanced simulator that is available to the industry, which is TCAD Centaurus. Maybe I wanted to give you a homework at some point to test out and find the cost of Centaurus license or something like that. But anyways, I didn't get a chance. But my point is it's actually a really cutting edge tool. It has a lot of capability and most people in industry use this to design the next generation transistor. And I will have you work on not MOSFET, a more cutting edge device called FinFET. I don't even talk about FinFET in 335. I do talk about FinFETs in 433, but we just briefly have 1 or 2 lectures on FinFET and then we go back to MOSFET because we don't have the PDKs, process design kit for FinFETs available here as of yet. We are working on it. We're trying to get it. But you see the point, right? We haven't even touched upon FinFET, but you get to make a FinFET, which is a more advanced device, even more advanced than the conventional bulk MOSFET, as you see. So hopefully you'll have fun working on it. It's probably not going to take too much time, maximum 2 hours to 3 hours. I think 2 hours should be good enough. This is more like following along a tutorial. Like, okay, do this, do this, do this. When you start from scratch, you end at a fully functioning FinFET structure. You see the 3D structure. You see the IV properties, IDVGS, IDVGS, and band diagram as well. So hopefully this will be a nice experience for you. And I made it optional because if you simply have too much on your plate, just ignore it. It's okay. You could do it later on as well after we're done with the semester. Okay, no pressure. But since I'm giving it as a homework, it makes sense to have some points. Obviously, it's gonna have some extra points. So if you want to if you do it, it's probably gonna add a few points. I'll mention all those specifics in case you have less points in any of your homeworks or exams and stuff like that. This will help. Okay? So give it a try. And this is actually one of the homeworks or one of the labs that I used to have for this course. So then I decided, I told you the story already, right? I changed all these labs to switch to the 336 themed labs to help you transition easily to 336. But this will actually give you an idea of what I originally intended to have in 335. Okay, moving to the next concept. Today we will have a very quick lecture. I'll just brush up on a few concepts, take some questions. It could be a long lecture if you have questions, but if not, then it's probably going to be very brief. I already uploaded a concept map. Please take a look at it once you go back home and check the canvas. The reason why I didn't upload that concept map at the beginning of the semester was because I've seen a negative effect on students. When you go through all those complex terms, chronic penny model, whatever, it tends to scare the students and they feel like, oh, it's not for me. It's probably not, I don't have the background. So I typically, for all of my courses, upload the concept map at the end of the lecture, not at the beginning of the lecture. Okay. So now you have the concept map. Take a look at it and see whether those concepts make sense to you. The reason why I wanted to have those keywords is because it helps you solidify your confidence in a way that, oh, I managed to go through all of these concepts from beginning to end within a few months. So I'm capable enough to pursue this direction. So take a look at it. If you feel like something doesn't ring a bell, then you can talk to me, or you could just review the lecture corresponding to that portion. Finally, what else? Did I miss anything? I don't think so. Okay, maybe I all the lecture recordings are available on Canvas. I realized that for just one lecture, I forgot to share my screen, and that's why it's just audio and no, visual. So what I'm gonna do is, because this is part of your final exam, I will re-record it at home and I'll upload it. You don't need to worry about if you don't know which one I'm talking about. It's okay. Enjoy Thanksgiving, and by the time you get back to studies, it will be there. So you have all the recording lectures available for your final exam preparation. Final exam will be similar to the midterm in terms of the types of questions that you can expect, in terms of the approach, open book, open everything, ChatGPT, whatever, right? If you can use ChatGPT to solve those questions, that I'll be glad. And by the way, don't trust all of these AI systems blindly, because they will just give you any answer that it feels is right, but it may not be right. Anyways, so with that, any questions from your side before I get started with today's lecture? Questions? Concerns? No? Yes. Mhm. That's a good question. Not necessarily only Venn diagram. I will also focus on the IV property, current voltage characteristics. Okay, so ID VGS, ID VDS, and for BJT is the same. Like you have, as you know, like similar properties. Venn diagrams will definitely be a part of it. Sadly, at least for this level of and we'll talk about the levels of abstractions today. For this level of abstraction, Venn diagrams are basically the king. So there will be a lot of Venn diagrams. There will be a lot of true-false questions without Venn diagram as well. And pay particular attention to the true-false, because I typically tend to have negative marking for them to avoid somebody randomly picking all true or all false. Okay. And what else? Other than that, I don't have anything extra to add to that. I know that for the midterm, the homeworks helped, because that was the idea. Because this was the first exam that you're taking, I wanted you to be more confident and better prepared. But midterm could act as a guideline for your final exam. And if anything, I hope you know by now that don't need to worry about memorizing anything, right? Please pay attention to understanding. And honestly, that's the whole point. If you understand something, it will stay with you. You will forget the concept, you'll forget all these equations, you'll forget probably the Venn diagrams as well. But if you know the logic behind drawing them, you could start from scratch and revisit at any point in your career. That's the whole point. And by the way, after you review, if you have questions, I'm available here to help answer. Yes. Yes, absolutely. Great question. Yes. You must have noticed that I deliberately had the submission deadline before the final exam. Is that right? The reason is I plan to upload we have the recording already. I plan to upload the recorded solution right before, like on the same day, so that you could just review it. But use it as a, preparation for your final exam as well. Why not? That will help, obviously. Any other question? So I'll upload the solution as well as a recording explaining that. And hopefully that helps. But if you need to talk to me, you're welcome. All right. Any other questions? Not necessarily about the logistics. Any other technical questions? Like something that you always wanted to ask but never got a chance to ask? Okay, if not, you know where to find me, right? I'm not going anywhere. So, well, before the final exam, of course, even after the final exam, I keep interacting with my students every once in a while in the lobby. Like, okay, they have a question, they ask me. So always feel welcome to come and ask questions. Anyways, so looks like the slides are ready. Let's get started with them. And the reason why this is probably going to be fully non-technical. This is more like a concluding slide for the overall course and hopefully give you some perspective in future. So I would like to start with a video that shows what happened to the semiconductor industry over several decades. And some of you who attended my 395 seminar, you must have seen this particular video before. But I hope this gives you a message, whoever hasn't seen it before. This is where the semiconductor industry was in 1990s. As you see, the top two positions were taken by Japan. Intel was there. Intel was climbing up steadily, and it rose to the top. I want to show you that this field is extremely competitive. If for some reason you're complacent, if you're not innovating for a year or two, it's very easy to fall down in the bucket. Okay, so I will make a point afterwards, but maybe take a look at it for a few seconds. And again, it's going to be tricky to upload this recording today because I'm using other videos within these videos. I don't know whether YouTube will have any copyright issues with it. In that case, I'll have to share it separately with you all, but we'll see. So you see, Samsung was rising as well in 2000. Before that, Samsung was nowhere to be seen, but they were rising up eventually. See, they're in number 4. In 2001, they're in number 4. ST Microelectronics, like a European company, it rose up. All on a sudden, Samsung became number 2, right? And then they're rising again. All these other AMD, Advanced Micro Devices, AMD, you must have known, right? They were like underdog at some point, but even in 2005, they're rising. Do you see NVIDIA anywhere? No. So, well, they're not even in the picture. Micron Technology, I don't know if you noticed that. They're one of the bigger players in the US right now. They were in number 15, early 2010s or so. So Micron Technology, I'll talk more about them. How many of you have heard about Micron? I'm surprised, but thank you. That's good. But this is normal to not hear about companies like this. Qualcomm, they were a startup, by the way, at some point, but now they're the big dog in the business. So everybody buys chips from Qualcomm, including Apple. See, they rose to the number 3. Starting in 2010 and beyond, like as a startup, they became so competitive. And Micron is in number 4 at this point. Hynix, this is a South Korean company. They're doing much better now. They went above Micron even, as you see. So 2016, not too long ago, not even 10 years ago, right? It will stop at some point. Notice Intel all of a sudden lost its first position to Samsung in 2017. So apparently for a long period, US led the industry with Intel and other companies. But now this is not even the most up to date. You don't see TSMC anywhere in the picture. TSMC is the top chip maker in the world right now. And honestly, Samsung is more like a dwarf compared to TSMC at this point. So just imagine how this, I don't have the data beyond this, so I cannot show you, but things changed dramatically. Within 2 to 3 years, things could change all on a sudden. So the point is, as when you go through your career and get to a stage where you work for a company, always keep in mind that you are basically going to decide on the future of not just the industry, but also the country. Because whoever leads semiconductors, as you can imagine, semiconductors are the driving force behind everything. People use this terminology quite often. Data is the new oil. There was a time when oil used to control the economy of the world, like whoever has most oil becomes the dominant. But gradually we're shifting away from it. Data, like Facebook, Google, they have a humongous amount of data. They are sitting with this data, and they can do a lot of stuff with them. So they are, they have a competitive advantage. Similarly, semiconductors are becoming the new crown jewel. Whoever has the most advanced semiconductor technology will probably control a lot of dynamics in the future. Imagine if you don't have the most advanced chips, you will not have the most advanced defense, for sure. It's not about the quantity anymore. It's about the sophistication, how sophisticated your technologies are, not just, how many you have. It's not sword fights anymore, as you can see, right? Similarly, you're not going to have the most advanced healthcare, right? Healthcare and so many other things are related to chip design. So innovation in this domain will definitely have a far-reaching impact. I want to show you a video as to how we go from sand to silicon. So this is literally sand, okay? So you take the sand, you melt it down in a crucible, literally melt it down, okay? And you cut them into small circles. And these are called silicon wafers. They are silicon, basically made of silicon, pure silicon. And then you use some sort of doping, like basically a chemical process to dope and make them into N-type or P-type semiconductor. And then you use light to create patterns. So when I say making MOSFETs or BJTs, they're all made with lights, okay, to maintain highest precision. So after you create that pattern, this is again doping. You start with a type of silicon wafer, but on top of it, you might need other types of doping, like P, N, P, one doping inside another doping inside another doping. So you keep doping this over and over again. Then this is like another chemical process called etching. You use different chemicals to, it's kind of like you draw something and you erase something. You erase with etching, you draw with patterning in lithography. Like the light-based patterning is called lithography. So all of these are like minuscule details, as you can see. So this is a very sophisticated chemical process, a lot of chemistry involved in it. All of these are minuscule details. And remember, these are smaller than virus and bacteria. And you're controlling them. You're making trillions of them simultaneously every second. So this is more like adding metal on top of the structure that you're creating. Because anything that you create, MOSFET, BGT, you have to add metal on top so that you can have external connection. Okay? This is an important part. Only a portion of the metal remains. And after that, you create a highway of interconnects to connect these billions of components. You see, you have to make sure all of them are connected. You easily run out of one layer. After that, you have to go to the upper layer and the upper layer and the upper layer to make sure they don't get short-circuited, okay? And then these are all your chips. These rectangles are individual chips. You cut them out like you cut a pizza, for example. And literally, you use this type of blade. And then you package them. This is another important part. Packaging is a big part of the industry, which makes it usable for the wider community. So you only see this external package. You don't see what's inside that. And obviously, before you ship it, you have to test individual chip and then market it as a product. So despite us being the user of this thing, you will hopefully get an opportunity to work at the very core of this technology where you make that stuff. That's where the challenge lies. Not everybody could do that. But this is taking credit goes to Intel for this video. This is basically their process, but every company has their own process and they're different from each other. Apparently, you could sell your process. I remember, and don't quote me on these numbers, by the way. I remember that Global Foundry, they're also a big foundry, not the topmost foundry in the world, but they're US based. So they have a very big role. They bought their technology, like 14 nanometer transistor technology from Samsung. So basically, they tried to develop it from scratch. They realized it's impossible to catch up. By the time you develop 14 nanometer, people will move to 7 nanometer. So they bought it from Samsung. And I interned there for about 6 months. And at the time, they were looking at 7 nanometer technology. Okay? And it was so difficult, they eventually failed and they gave up. They basically laid off thousands of engineers all on a sudden. They realized that, oh, we cannot do it. It's so tough. So if you have a competitive edge in this domain, it's very difficult to catch up, but it's not impossible. You just saw that. right? At some point, Intel was so dominant, nobody even thought about even catching up with Intel. Intel was the company who invented chip design. But now, again, they're trying to, yes. Yeah. That's a great question. Great question. Honestly, this is a question that everybody is asking, but nobody has the answer. Okay. So apparently, we are now looking at 3 nanometer. In fact, IBM claims that they have 2 nanometer like. So IBM is a company. It's an interesting thing. They don't really. Have you ever seen IBM chips? Like basically, you use Intel chips or TSMC chips. IBM don't sell in bulk. They basically sell the IP. They invent something and they try to sell the IP. So they are not really a big chip maker, but they also participate in the chip technology development. So they claimed several years ago that they have 2 nanometer functioning. But as of now, 3 nanometers are being pushed in commercial products, as you know. Like you must be getting stuff from Apple. So 3 nanometer is small enough. In 433, I have a slide. I don't have that slide here, where we count the number of atoms between the source and drain of a MOSFET. And I told you the count came down to be few tenths of atoms. And that's an old technology. So in the most advanced technology, it's already few atoms. What's next? So people talk about if you keep making things smaller and smaller, quantum effects will basically kill you, and they're actually killing us. So we are using quantum to control quantum. So, the FinFET structure, which I didn't get a chance to talk about, obviously, it's not supposed to. 335 should be the very basic foundation of device knowledge. But FinFET has a lot of quantum effect in it, which we have to deal with, including fin quantization and so on. Again, I'm not going to get into the detail of it. So as of now, nobody has the answer as to what can we do. We have pretty much exhausted the capabilities of semiconductors, honestly. So people, I heard it from an Intel engineer that we have tried almost every element in the periodic table except the ones that are radioactive and try to find ways to make the next devices and stuff. So right now, people are looking at superconducting electronics quite seriously. There was a time when it was like, I don't know, science fiction. Even when I was a kid, we used to think of science fiction with superconductors. But now, not anymore. People are actually making circuits and systems with superconductors because they give you lossless conduction and they have some interesting physics. So we are going beyond semiconductors at this point and trying to look at other opportunities. But until that happens, we're kind of stuck at the atomic level. And by the way, just to also add, sorry, I don't want to get started with that video before I conclude answering that question. Where is this? This is a stable slide without video. So where is I? Yes. So remember that portion of the video where I showed that you use light to create patterns? What we do is to create smaller patterns, you need to use specialized light. So from ultraviolet, you go to UV, and then we are now doing EUV, extreme UV. So basically you make specialized light with shorter wavelength to create smaller patterns. So we are basically going to extreme UV already. We're using extreme UV already, right? If you try to make smaller, even smaller features, we'll have to go beyond that. So that's also already a challenge. Extreme UV machines are extremely expensive, hundreds of millions of dollars, for example, one single machine. So you can only imagine how difficult it is to go beyond that. So that industry, you might be wondering, okay, how is that possible that these big tech companies don't have an answer for it yet? And that's exactly the worrisome situation. Nobody has the answer. If you go to conferences, they talk about post Moore's law. Is Moore's law dead? Is like, I mean, what's next? They have a timeline. Obviously, Intel has a timeline. Everybody has timelines. It's very difficult to meet that timeline now. So we don't even know 5 years down the line, how are we going to manage, honestly? So that's why there is a very big push in research as well as investment in R&D within the industry and beyond. Okay, so you asked a seemingly simple question, but it is a very deep question that in the industry is struggling to answer. What's next, honestly? At some point, I don't know, we must have already gotten used to not seeing too much hardware improvement from most of these chip makers or Intel. We have been seeing Core i7 for more than decades, in fact, decades now, right? Don't you think? But think of the earlier generation. I don't know if you remember Pentium processors or Celerons or Core i3, Core i5, Core i7. We quickly accelerated through them to Core i7, but now almost saturated. Okay, did I give you an answer to? Okay, all right. Finally, I just want to show you an interesting video about the uh, you know the top chip maker in the world. Yes, yes. Amazing question. I think this is probably one of the best questions that I've received in this semester so far. It's a very deep question. There is a field called yield engineering. Yield. So basically, when you make chips, and you've seen how sophisticated this technology is, not everything will work. So typically, your yield could be 50% to 60% to 40%. When you start developing a technology, only 20% might work, and 80% will be, oh, they're not working, because you cannot control them so nicely with simple chemicals. You see, we are basically using chemicals to etch away, like acids to etch away stuff, and we are using light to create pattern. But it's kind of like doing carpentry or like some sort of artwork, that you have to make some layers, etch some layers out, and then create some more layers on top of it, deposit more layers on top of it. Just pure chemistry, honestly, but chemistry controlled with sophisticated machines and robotics. Okay, extremely sophisticated. Nobody does it manually, as you can imagine, right? uh, so first of all, before we go and make this stuff, how do you know that this is exactly how we make this device? Can you imagine? Like, is it even possible for us to test it out? No, because something that here's the catch: something might work on a higher level, like when you try to test them at scale, at a higher scale. But when you make them smaller, one material may not get into another material because of viscosity related issues, because of other adhesion issues. So the properties of materials will change at nanoscale. Interesting. Okay, so we simply cannot mimic that feature in a larger scenario and possibly hope to repeat that at nanoscale. So that's not how it works. So we rely a lot on, guess what, simulators. We use highly sophisticated physics-based detailed simulation tools, and that's why these simulation tools are extremely expensive. Okay, how expensive? I mean, if I can give you a little more information, many national labs don't have access to these tools. For example, we collaborate a lot with say Lawrence Berkeley, Sandia, obviously Oak Ridge is like next door, and other entities. They don't have access to the tools we have. And you might be wondering, are you guys so rich? Like, how can you? Because we are a university. They basically give it to us at a subsidized rate. The university can afford it. Why? Because they want us to teach the next generation. If nobody knows how to use these tools, then who will buy this tool eventually, right? So we need to teach you how to use them, so that you can go and work for those industry and use them, and thus industries could pay big bucks for the actual tool makers. Okay, so there are companies like Cadence who make tools. Only thing that they make will be these softwares, but these softwares are so powerful that I don't know if you remember when there was a chip sanction, like trade war kind of stuff, and the US government sanctioned some other countries from using these tools. So just imagine, you are sanctioning a software to be sold to a country. So how critical that software is. Like, just imagine, you cannot give this software to some people, because otherwise they will beat us into something. I don't know. So you see, so these softwares are so sophisticated. They used uh, deeper down quantum mechanical concepts, so that you have a very accurate prediction. So you simulate over and over again. You are absolutely sure that this thing is going to work. There is a 95% chance. And then you go and make stuff. Even then, things don't work because you cannot properly control everything with your robotics. Okay. So as long as you have some yield of 50% and above or 60% and above, this is commercially viable. So that's why some chips are more expensive than the other. So if you buy or make a chip in previous technologies, these are called legacy chips, using older technologies, they're gonna cost you much less, like $5,000 maybe for a chip, to make a tape out a chip, $5,000. But if you do it in the most advanced one, it could be more than $100,000. So that's the difference. Why? Because the previous generation chips We have tried them, tested them. Their yield is very high. We could make almost all of them work. So you don't have any loss. But imagine the most advanced ones could have a yield of 50%. So you'll probably have to pay for the remainder. So you have to add the cost to the ones that actually work. So it becomes more expensive. But the people who buy these most advanced chips, they don't care about the cost. So you pay more than $1,000 for an iPhone, but you'll not pay $1,000 for a toaster oven, for example. Or the fighter jets, right? They need the most advanced technology available. We don't care how much it is. But you will probably not use it for commercial aviation, like, American Airlines, Delta. They want to cut costs as well. So you'll see many of these equipment, like if you ever see the cockpit of like one of these domestic flyers, you see this looks low tech because they're cutting cost. But the other ones, obviously, fighter jet will have the most advanced one. I heard that even a simple helmet could cost more than $1 million because it's probably going to be so advanced. So there you go. So they lose a lot of these chips that they make. And that's actually a part of in 433 I have a lecture where there are 2 slides about calculating this cost. There's a fixed cost, there is a variable cost. So the fixed cost is how much it takes for you to do the R&D to make it work, and that could be more than $1 billion. And when you sell your product, you sell so many of them, you add those costs to it so that you eventually win over. Does that make sense to you? Okay, so I'm going to show you a quick video, like 2 minutes, I think, that shows, it talks about TSMC. Yeah, because why am I showing you this? I think you should be aware of what's the cutting edge, rather than just staying in the dark and realizing too late and waking up and realize, oh, it's too late for us to catch up. Let's not do that.
Over 30 years, Taiwan underwent massive industrialization.
Okay, so ignore this for now. I will upload this video or share this separately because I don't know how to, deal with the audio. Maybe can I turn on audio? Let's see. It's not on mute. The audio is active. But I'm hearing it in my AirPod. So, okay. Here is what I can show you the video. I can explain it myself, and I can then share it later if you're interested.
In what has become known,
so basically, this is TSMC in Taiwan.
Miracle.
Okay, so this is a BBC documentary. There's BBC, courtesy BBC.
Names, ASUS, HTC,
so someone,
Acer.
A reporter from BBC went in, and she's gonna go inside the
semiconductor industry,
the actual
led by a
foundry
company
where
you've
they make the
probably
chips.
never heard of.
So she's saying that you probably have never heard of this company.
It's one of the largest
I mean, that's
semiconductor
true,
manufacturers in the world, producing the chips inside some of the best phones.
This is the silicon wafer that I just talked about. Intel does the same, but underneath
if you have a smartphone,
this silicon wafer, the technology is very different. They look similar.
And these
Everybody
chips
uses silicon
were only
wafer,
made possible thanks to the discovery of
the underlying
semiconductors.
technology process of making these chips is very different.
Important or interesting?
So
because
some discussions about why they are important and interesting.
With
Anyways,
factories
so
or
this is the
fabs,
fab,
as they are known across
you see
the globe,
all those robots,
the largest is here in Taiwan.
Carry the silicon wafers,
and we've been
like thousands of them. No human being will be able to handle it in a sophisticated way.
That form the heart of our electronic devices.
The reason why the light was yellowish was because they want to protect these chips from getting damaged. The chips are so sophisticated, they will get damaged simply from its, visible light. Like if you expose visible light on them, these devices could break down.
The start. So I had to put on a hairnet, wash my hands.
So basically, before you get into the fab, you have to go through a rigorous process, and you have to wear this,
But it is time for an air shower.
Clean room suit, and take an air shower. Basically, I had the good fortune of doing this in my grad school as well as an intern in Global
manufacturing of
Foundry.
wafers has to be.
We have a clean room here at ORNL, by the
precise.
Oak Ridge, CNMS, Center for Nanocrystal Material System. If you ever get an opportunity to go there
and damage the chips.
We do some activities for research there.
Finally, we were allowed in the factory, and there was a
there you
good
go.
reason
So
for all of
this
that
is known
fact.
as a clean room. It is clean. It is so clean that
these chips
you can count the number of
how many
particles in air.
transistors you can cram
maybe
into
class
a
1,
tiny
class
space.
10, class 100. They have
tiny,
some categories, some ranking. That basically represents how many particles you can expect to get in air.
I don't really know how to describe how fine.
Anyways, I know it's boring without audio, but
5 nanometer
I'm going
or
to fast
7
forward to
nanometer
it.
is.
But there are quite a few
basically,
things
these
we're
robots
not allowed to film
collectively
because
travel
this is seriously
more
cutting-edge
distance
technology,
than
so it needs
many
to
times
remain
around the
pretty
Earth in a day,
secret.
because they travel so much.
We have to protect our
within that
customers'
factory, of course.
information.
And anyways, so there you go. You see, again, I don't want to keep showing you robots. They couldn't
Concept
obviously
of keeping up with
take videos
Moore's
of
law,
most
as
sophisticated stuff
predicted
because
by
that's
Intel
kept secret. I just wanted to give you an example of how things are. So can you see this? These rows are all silicon wafers. So one robot is carrying all these silicon wafers. So it knows from which step to go where. So you have done etching, now you have to do deposition. Let's take it to the other machine for deposition. So this is automated. Nobody manually controls it, as you can see. What's the role of engineers there? Engineers come, you'll be surprised to see, most of them will be sitting in a
a
desk
concept
simulating and
increasingly hard to
designing.
keep
And after
up
you
with,
design, you just,
despite
it's
us
like
expecting
printing
a lot
something, right?
more from our ever-connected.
Maybe you make a really nice document. After you make it, you just hit print and it prints. The printer prints it. You don't go and write it anymore. There was a time when people used to manually write things similar. So now we design the chip using softwares, and that's exactly what my idea is. In terms of the homework that you're doing, you design the device. After you design it, you just send it over like you are printing to these machines, and they make it in billions. You just have to make sure you do a really, really thorough job in your simulation. Anyways, I'm just gonna fast forward through this. Okay, before we end, we have a semiconductor characterization lab here at UT. Professor Rose and I, we jointly run this lab. If you are interested to see how things are measured, like for example, if you have a really nanoscale tiny device, how can you measure individual devices? I talked about IDVG, measuring drain current versus VDS, drain current versus VGS. How do you measure individual devices? Like, that's the question, because they are so tiny. How do you probe into them? So you have these sophisticated machines. They're called probe stations. Of it, the name suggests what it does. It has probes that are highly sophisticated. You use a microscope to zoom into them, and I don't know if you can see this. Let me see. Yeah, so these are probe tips. See, they're like obviously zoomed in, magnified. So you use these tips to connect to different devices and measure them. Obviously, this machine costs more than $1 million, for example. So it's very expensive and sophisticated machine, but it allows you to test individual devices. For this video gets into the detail of it. It's available in the same channel that you are getting if you're interested. We organized a lab tour for a lot of kids that came from all over Tennessee, and we showed them the lab and showed them how things are measured. Again, if you're thinking chip design is too difficult, it's not for me, think twice, because I keep telling this over and over again. We have a program funded by NSF, which started this year. Professor Ali Fatih and I, we started this program. So basically, we teach chip design to high school kids. Why? You might be wondering. Well, NSF, the nation realized if you don't start soon, it is probably going to be too late. Okay, if you don't get these kids into a direction that builds towards chip design, semiconductors, now we will have a competitive disadvantage moving forward. There are many countries who are at the top and they are nowhere in the picture anymore now, because this field is so competitive. One innovation could change everything. Like everything else could be obsolete. Just one innovation. So you need a lot of people working in this domain. So they are targeting high schools. And you see this room full of high school kids mostly. If you like, we have a lecture series which starts from ground zero, assumes absolutely no knowledge of, and this is basically KCL, KVL being taught to the students, as you see. And from there, they will go and make a chip, like literal chip, and tape it out and test it. So we have gone through half of it. They have made hardware. They've made a sensor system which detects, some stuff. Anyways, but the next step would be to actually design chips. So why am I showing you this? To inspire you. If they can do it, I mean, you are definitely at a much better situation than them. And I keep saying over and over again, don't let these boring lectures derail you from taking this up. Maybe these lectures are boring, maybe others are not, right? There will be situations where things are not so appealing, but there are appealing sections in this paradigm in general. I have shown this before, but I want to revisit at the end of this lecture. There is a level of abstraction. The conceptual level of abstraction is very vital for your understanding of chip design industry. What you have done so far, we have done together so far, is focus on the devices. We have seen one kind of device, which is basically transistor, BJT or MOSFET. both of them end with T. T stands for transistor. Transistor is just one type of device that we use. It's not the only device, okay? This is easy enough for us to talk about. Remember, we built from diode to BJT to MOSFET. So there's like some degree of hierarchy. There are so many more devices that are being explored right now, and that also adds to the question, that we were asking before. If the transistor is getting so small, what's next? So, well, there are smaller components than transistors. Nowadays, in industry, transistors are considered to be big. Like, they're so big. Can you imagine that? Like, we're talking about transistors being super tiny, but they are considered to be big and bottleneck of area, because we have other devices that are much smaller than transistors. I'll take a few minutes to talk about it in a second. But notice this memristor. These are superconducting devices, but I don't want to get to that. But even with conventional semiconductors, room temperature stuff, there are devices like magnetic tunnel junction and phase transition material, memristors. They are nanoscale. They're super tiny compared to transistors. So whatever, transistors are switches. We consider them to be bigger switch. Imagine that, because we have much smaller switch than transistors now, like much smaller, many times smaller. Okay, so we use those devices. We are trying to use those devices as switches instead of transistors to save area, so that we could fit in more and more components. Okay, so what I'm trying to tell you is there are other type of devices that you haven't seen here. Will probably not be covered in any course that you take, honestly, because these are being actively developed. Maybe they were developed last year. So who will write a textbook and prepare a course? By the time I prepare a course, they will move on to a new device, right? This will become obsolete. So the only way to stay current with this would be, first, one of option would be to work in the industry and see what they're doing and be part of it, or do research. And when you do research, you actually work at the cutting edge, even beyond cutting edge. You think of what's the future. So to think of the future, you have to know what's here now. You cannot just stay within the textbook anymore. Textbook helps you develop the basics, but it is far away from the cutting edge, honestly. Okay, so after you design devices, there are interesting ways to use these devices to design circuits. So you have seen an amplifier, by the way. I think we're working on one for Lab 6, right? Just a single transistor amplifier, but there are more complicated, more sophisticated amplifiers. The amplifiers that could sense millivolts, amplifiers that could sense in cryogenic temperature, and blah, 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 right? They're noise immune, different features. So there is a whole host of innovations and strategies that people use to design amplifiers. And they're just one kind of circuits. There are different kinds of circuits that compute, circuits that store information, circuits that amplify, circuits that sense information, circuits that help you convert one level to the other. So many different purposes. So you are just looking at one type of circuit. I just want to show you the vastness of this domain and the opportunities. If you don't like one, maybe you like something else. It's okay. All right. Anyways, moving to the other one. After you design circuits, you use them to design systems. Eventually, there are people who work on high performance computing at ORNL. I don't have to tell you more, because the most powerful supercomputer used to be here, not anymore. I think it's in a different national lab now. It's number 2, I guess. It's very recent news. Maybe a couple of weeks ago it changed, but this thing will keep changing. So now they will buy a bigger one. Anyways, so HPC, high performance computing system, it's not just supercomputer, by the way. Facebook has data centers that you are all using indirectly as users. When you upload a photo or whatever, it goes to their data center. Google, when you do a Google Maps search, that you're basically using Google's high performance computing system. So you're a user, but somebody has to make these systems and handle them. So high performance computing to neuromorphic computing is the future, basically brain inspired computing. It's kind of like learning from how the brain works and bringing that into hardware. By the way, there is a level below the device level that we didn't really talk about. Typically, this is the focus of material science department or chemistry, where they deal with materials. But even in electrical engineering, nowadays the barriers are being broken. Like, there are a lot of folks in electrical engineering who focus on designing materials. So if you think of a new material that could dramatically change the game. For example, when I was a PhD student, I never worked on superconductors. When I started as a faculty here, I was fascinated by the properties of superconductors that some people were working on. Oh, by the way, during my PhD, I worked a lot on ferroelectrics, phase transition material. In fact, my PhD thesis was based on phase transition material-based electronics. Okay. Does anybody use it now? No. What's the point? The point of doing PhD research is to think of something that people will possibly use in 10, 20, 25 years, not to think of the next product. Am I making sense? That's the difference between industry research. Industry research is quick, targeted, and obviously driven by finances. Like, what can you sell in the next 3 to 4 years? You have to sell, otherwise the industry will not survive, right? Academic research is open-ended, like dream of something that will probably make something work in near to distant future. 10 years, 20 years, 30 years. I told you the story that somebody dreamt of MOSFET in 1925, right? More than 50, 60 years later, it was realized. So it could be even that far. But honestly, we try to keep it a little bit closer than that. My point is, after I learned about superconductors, I started, using them in making circuits and systems. And now, like, many of our works have led to, some interesting circuits and systems with superconductors. So you see, like, if you have a new material system, that could dramatically change your approach towards designing the next level of electronics. Okay. Nowadays, a lot of people are working on 2D materials. You don't know what they are, I guess, but have you heard of graphene? Graphene is a 2D material. Or how many of you heard about carbon nanotubes? Have you heard about it? It's like pillars of carbon atoms, cylindrical. If you just imagine, just visualize it this way, if you just cut off the cylinder and just flatten it, put it on a surface, what you get is graphene. Interesting. Or how many of you know about graphite? We all use it in our pencils, right? Graphites would be like layers of graphene, essentially. If you could separate out one layer of graphite, that's graphene. That's how the name comes, by the way. And quite literally, that's how they were invented in England. There was a group of scientists who used duct tape, literally. They used duct tape and took it out, and the tape only took out one layer of graphite, and that became graphene. They invented graphene, and it became a marvelous discovery. Now we don't have to use duct tapes anymore. We have other processes to make them. But they got Nobel Prize for the discovery of graphene. Just imagine how much impact it has to have to get a Nobel Prize. Anyways, so what I'm telling you is discovering new materials could dramatically change the game into the next levels, completely change the possibilities. Why are we interested in superconductors? They have absolutely zero loss. Metals have loss. Metals are good conductors, but they're not the best. Superconductors are best. What's the catch here? As of now, we don't have any room temperature superconductors. So you need to go cryogenic, cool them down in like very expensive process. Anyways, moving to almost the last slide. I want to show you the domain of electronics in general. Computing is a very big aspect of electronics. When we make computers, I've been talking about Intel. What does Intel do? Intel makes processors. Processors process information. Process and computing is basically the same thing. You process information. You perform NAND operation, NOR operation, XOR operation. You might be wondering, okay, what's the big deal? When you use XOR operation could be used to add stuff. I don't know. Maybe if you remember, A XOR B XOR carry in is the sum function. Basically, that's how you add numbers, if you remember Boolean algebra. Anyways, these small building blocks lead to bigger processors. So computing is a very big aspect. So far, whatever you have learned in this course, they all gear towards computing. How can you compute? How can you make NAND gate, NOR gate, stuff like that? Okay. Amplifier is a circuit that is ubiquitous. They're used everywhere, like in computing, in sensors. Like if you sense something, but the signal is not really high enough, you amplify it. So amplifiers are like kind of ubiquitous. They're used everywhere. So amplifiers help you touch over sensors. But there are other opportunities, including sensors, memory, and so many other. I will talk about them later, which we haven't touched, but they're all fascinating. Like, how do you sense some physical information like temperature, light, intensity, or vibration, magnetic field, whatever, presence of something like proximity, and convert that into usable electrical signal that you can process. So you sense, you create it into electrical signal, and then you process using computing. By the way, you have to compute and make sense of what you're looking at, right? So just imagine that. The electronic systems bring all of this together, by the way, all of them together. I'll give you one example of that finally. Memory is a very big part of a computing system. Without memory, no processor can work without memory. Imagine when you, like, if I ask you to like do this compute, multiply this with 13, subtract with 10, add 2, and multiply with 10 or whatever. Like, I'm just adding something. If you were a kid, like when how the little kids calculate, they will probably do this, calculate and put some number here, and then do the next step, and then do the next step. Notice, unknowingly, you are saving this information somewhere, and then getting to the next level, and then saving that information somewhere, then getting to the next level of computation. So we have to keep saving that information somewhere to get to the next level of computation. But interestingly, that's how computing works. You process some information, you have to store it somewhere for the next level of processing and the next level of processing. So without storage, there is no computing. Okay, you have to store the information that you will compute with. Where is A and B? Where will A and B come from? They will have to be stored somewhere. And then after you compute something with A and B, where will you save the output? You have to store it somewhere. So memory is an inseparable part of computing system. There is no computing system without memory. Even in processors, Core i7, for example, there are built-in memories inside the processor. They're called cache memories. You'll see in the specs, like this much cache. Okay, and beyond cache, there are storage plus memories. So memories are a very big part of electronics. In systems like, think of autonomous vehicles. You have to keep sensing your surrounding, take in information. So sensors are in play. You already have some predefined features stored in the memory. So obviously without memory, you cannot do any computing. So after you get the sensor data, you have to process it right there on the fly. So you have processor, storage, sensor working simultaneously in one simple example. Okay. Moving forward, this is the next level. You probably don't have any textbook yet about any of them. Doing computing and memory using separate blocks is not cutting it anymore. We used to buy RAM and processor separately. Core i7, 32 gigabytes of RAM. We still report it this way. But now we have a trend where people are merging processor and memory together. Even Apple is already doing it in some of their commercial products, because it takes too much time to bring the information from memory to the processor to actually compute. So now they're merging them together. This is the compute in memory field that is kind of getting a lot of attention right now, especially for AI. Similarly, in-sensor computing is getting a lot of attention. Just to, like, we are working on this domain a little bit. Think of pixels. Like when you take a photo, you have, like, we talk about a 10 megapixel camera, right? What are pixels? Pixels are tiny circuits, small circuits. They use, interestingly, some sort of PN junction, but reverse kind of image sensor junction that converts light information to electrical signal. Okay, and then you have some circuitry to handle those signals. So imagine when you're trying to track a missile, for example, a missile with one of these cameras, you're trying to track it. It takes some time for you to send that image information to a processor to process, and the time is about 1 millisecond. 1 millisecond. Okay? Within 1 millisecond, a hypersonic missile moves more than 10 feet. So by the time you, got a photo, let's send it to the processor. By the time you send it to the processor to even think of what to do, the missile is not there anymore. It has moved. And by the time you finish processing, it's like probably, farther out. So that's the reason why it's extremely difficult to track and, obviously counteract with hypersonics right now. People are realizing this now, that, our systems are too slow. So let's not wait and send that information from the sensor to the processor. Let's process it there in the sensor. So that's why this is just one example that I'm giving you, obviously. This in-sensor processing is hitting up. Think of, Teslas drive themselves now, right? They have cameras, they keep capturing images live, and they send those images to a processor, and the processor decides, is there a car? Is there whatever is there, right? And there is a lag between the sensor sending that information to the processor. And by the way, more importantly, it's capturing all of this information and sending to one processor to decide. What if that processor freezes or, miscalculates or does something, right? There is a reliability issue in the processor. Then you have a problem. And more importantly, cyber attacks and all sorts of other concerns are there when you bring all of these into one processor. But imagine if every camera could make a decision, make a call within themselves, and then send the information, have the processor verify your call. Like, hey, I think there is a guy sitting there. I don't want to drive over this person, right? But what do you think? Am I right? Like, maybe send the information to the processor as well to make a second call. So that's the other direction that people are going in, redundancy. So making a call within the sensor, deciding whether there is something, and then doing processing again in the processor to add a layer of security. Anyways, so that's where people are headed as well. All right. Anyways, I hope I didn't bore you too much. The point is, my only intention is to show you the vastness and possibilities of this, field. If you don't like something, maybe you like something else, but I'm sure you will like something in this domain. So please consider staying and contributing, and obviously invest in yourself to learn more and train up for the next generation. And this is something that I really like. The best way to predict the future is to invent it. So I want you to not just learn about what people are doing, but do something that other people will learn about in future. Okay, and you can do it for sure. Trust me. You just have to trust in yourself. That's all. Okay. All right. Thank you. I don't have anything else to talk about. That brings us to the close to this semester. Thank you for all of your hard work and patience and everything. I hope to see you around on campus. All the best from my side, and you know where to find me. If you have any questions now or later, don't hesitate. Okay. Thank you.